So far, what I've done is try to give an introduction to ceramics, done a rehash of some of the things that you know, some of the things that you may not know. And now I'm getting down to the real course. Today I shall start off with comminution and grinding of materials. You see, what have we learned so far through the previous lectures is A, we require particle size with a certain distribution so that I can have maximum packing. So that pores are smaller, open pores are smaller, and hence diffusion and sintering can occur faster. One requirement is as far as better packing, I require a certain distribution of particle size. Second most important thing we have learned is have as pure a product as possible, because there are impurities which may form liquid phase, and once you have a liquid phase, you have a material which is possibly undesirable in most of the cases. In real life, even today, if we consider by the tonnage amount of ceramic products that are produced, most of the raw materials are derived from natural sources. The window glass that you see is derived from sand. Let me take the case of the window glass as an example. What would they do? They would take the sand. If they take the sand as derived, they would add soda, some calcium oxide, some aluminum oxide, melt it, and then maybe form the type of glass panes you see. Here we would be faced with a major problem. Sand, as we obtain from nature, you have seen they are colored yellow. This yellow color is present due to the iron oxide. If this iron oxide is not removed, it would be very difficult to have a transparent glass. Today, we are at an age where environmental issues which should have been taken care of much more earlier are coming to the fore. How was this sand, which is yellow, was cleared of iron oxide? This iron oxide which is there cannot be removed by magnetic separation. So what was used to be done is the sand would be taken, crushed, and then reacted with acid. Whence the iron oxide inside the sand would dissolve in the acid, filter the acid out, wash the sand. This had been the practice. Now today the issue is how do you dispose of the waste? And hence because of waste disposal issues which affect the environment. Earlier people have disposed of the waste in the ground. Today it is unthinkable. So you got two choices. One, get as pure a sand as possible which has got low iron oxide content, or try to engineer the sand. For example, if you look at the absorption spectra, let me say this is 300 nanometer and this is 1000 nanometer, and let us say this is the absorption coefficient. If a glass is made from impure sand, what would happen? Fe2 plus absorbs in the ultraviolet range. As it goes more towards the visible, the absorption falls off, and then at the IR range Fe3 plus starts absorbing. So, this is Fe2 plus Fe3 plus. This glass would appear yellow. So, what people do at times is add materials which would absorb in this region, and as a result the absorbance would be flat, as if the glass is not colored. In places where that pure sand is not available, additives are added to the glass so that it does not appear yellow, though everyone does try to get as pure a sand as possible. But to come back to the main point, what I was saying is, in view of the environment requirements, many of the processing methods, beneficiation methods which had been in use 10 years ago are not acceptable anymore. In fact, they are evolving. That is a major issue. So, from natural raw materials, if we want to make a value added product, beneficiation is an important aspect, but one has to watch out for how to deal with the wastes. I said tonnage wise of ceramic products that are produced, the largest source is natural raw materials. Obviously, it will have a lot of impurities which will affect the final processing methods. Liquid phase may be generated. So, in many cases, we have to again purify the product. That is one thing. On the other extreme, where you are let us talk of optical, electronic or magnetic ceramics, which require ultra pure starting materials. How do you get them? Most of them are chemically synthesized. They add to the cost, they add to the value, but the end result, because we need such pure products, we will have to go to chemical synthesis. So, what I shall be dealing with is, one, how natural sources are processed, and second, chemical synthesis. So, if I have to talk of ceramic powder preparation, I have to talk of both of them. Now, before I proceed on this first one, natural sources, all of you have seen the way our highway construction is in progress. They take rock crushers. They are all around us. If you see the rocks which are used as ballast on the train tracks, they are as large as 6 to 7 centimeters across, while the stone chips which are used for making the roads are as fine as 5 to 6 millimeters. And those of you who have crossed the highways have seen the rock crushing operations. You have seen they have got crushers. Now, most of you, I guess, would have access to internet, and there is a lot of information available on the internet. So, what I would do is, what I have done over here is done a search of crushing machine from the Wikipedia. There are a huge number of crushing machines which are over there, and this is the commonest form of crushing machine. These are basically what are called our jaw crushers. What is over there is there are cylinders which has huge jaws, much like the what you see on your bicycle. Much like your bicycle, and these are rotating. If you look at this diagram over here on the screen, uh, if you look at the diagram on the screen, you will see that the feed goes through here. This is the belt. These are the big wheels which are rotated by the belt, and crushing occurs over there. So, without wasting time, what I would say is, if you simply talk of, say let's say jaw crushing machine, do your own search. There is no point in talking of books. There are huge number of jaw crushers which you will see are available. You can expand any one of them. This is the common jaw crushers used for crushing the stones. Now, if I am looking at how crushing can be controlled, you see on this side I have written feed size in micrometer. The scale, this is 10 to the power of 8 micrometer, means 10 to the power of 8 into 10 to the power of minus 6, means I am talking of meters. This is the feed size I have drawn over here. Now, no one takes 10 to the power of 8, 10 to the power of 2 meter stones. They are mostly over here. The jaw crushers which I talked of, over here I have got the product size. This is in micrometers and the scales are over here. So, 10 to the power of 4 micrometers means 10 to the power of minus 2 meters. So, it is a centimeter, and this way it goes finer. The area of operation of jaw crushers is over here. This is where jaw crushers are used. So, you have got the feed particles, the stones which are received from the quarries in this size range, down to 10 to the power of minus 2 meters. The jaw crushers are used extensively. In addition to jaw crushers, we have other types of crushers also which are used in ceramic industry. Rotary crusher. Basically, if I draw an out sectional diagram, what I will have is, this is the outer nozzle, and here there is a solid piece that keeps on, that is rotated, and the feed material is fed through here. By manipulating this distance, as this rotates, this feed material gets in and is crushed down to finer and finer sizes as it passes through here. Why does it happen? You have to remember, if this is a ceramic particle, let me say, this is a simple, okay, let me say this is a piece of stone that you find lying on the roadside. The first thing that I will see is, it has got inclusions. This is an inclusion, maybe a second phase. These are grain boundaries. These are grain boundaries. It may have pores over here. It may have flaws inside this. There is a crack hidden over here. There might be surface cracks also. Now, so I have got so many defects in this stone which you find lying on the roadside. It has got inclusions, it has got pores, it has got micro cracks, it has got surface flaws, so many defects. So, if I now crush this or apply pressure, one of these things will fail, and as a result maybe it will fracture into more pieces. So, that is why the advantage is, from ceramic raw materials we think of these crushing operations, as I have said, whether it is jaw crusher or rotary crusher, is each of these ceramic pieces, or that is a raw material, has its inherent flaws like I had shown over here. So, under impact they keep breaking down. So, over here after jaw crusher we have got roll crushers which operate say up to 10 to the power of minus 3 micron, because this is a 10 to the power of 3 scale and this is the product size, micron sizes. There is another type of crusher which is a very effective one, which is called hammer mill. Now, you see, let me say this, each of these descriptions you can find out by simply using your images form. I am using Google Images. Each of these can be, you can see on the net, expand them, look at them, investigate them. All these informations are basically Wikipedia based. What do you see over here? You see a rotor with 3 arms. Now, if you feed material from the top, as this is rotating, this whole rotor arm is rotating, these vanes are also rotating. So, as you have fed your material from the top, what will happen? As these rotate, all this material which is contained over here would be crushed at these spaces, and here what you have is a powder, finer powder gets out through here. This is one variation of hammer mill. There are many other variations which is also there. What I would say is this, look, use the Wikipedia extensively, it has got lots of information. This is another variation of the hammer mill. With the hammer mill we can get powders which are, this is the area of operation of the hammer mill. So, we can get here powders which are product size 10 to the power of minus 10 to the power of 2 minus 4 micrometers, pretty fine powders. But in all these cases, whether it is a jaw crusher or the rotary which was over here, you see, if I go back to the previous diagram, let me talk of this diagram and let me see what are the problems. This is a hammer mill, fine. Crushing will occur between these 2 arms, 3 arms as they rotate, as these 3 arms they rotate. Now you have to realize that as the hammer mill rotates, the ceramic raw materials are pretty hard. They will erode the surface of the hammer mill, and the powders will get contaminated with the material of construction from which the hammer mill has been made. This is a major problem of any crushing operation. Whatever, whether using jaw crusher, rotary crusher, hammer mill crusher, you will have the problem of contamination coming from the crusher itself. Now, the plus point that we have is here, most are made up of iron. So, frequently the best use to remove these iron impurities is magnetic separation. As the powder comes out, have it run through a magnetic field when the iron particles are segregated out. In any of these crushing operations, as I said, contamination is a major problem and one has to take care of that. The next type of powder which I will be talking of will be, let me scan it. What I did was ball milling. In a ball mill, what does happen? Let me blow up. This is all Wikipedia, open source, and hence I am using it. The copyright is open source copyright. Unfortunately, this is taking too long to open. Yeah. These essentially will consist of long cylinders in which what is done is balls are put in. This cylinder can be made up of iron. Frequently, these balls are hardened steel balls. Just think of a jar, steel jar, in which you have put iron balls and the ceramic raw materials that you want to grind down. This is how it operates. Fundamentally, as you can see, the jar is rotating in one direction, the ball is going up along the jar, and then beyond this point the ball falls off. There is a ball is going up from here through here and then falling off. The ceramic materials are getting crushed between the balls in a very simplistic fashion. There are much more details to it, and this is the simplest form of ball mill. This milling operation can be done in a jar which is 50 milliliter jar for laboratory operations to tons of material like the slide I had shown you before. Now, let me bring up another type of ball milling. You see, in the previous one, what I had was a cylinder which had steel balls in it, which was rotating. Here, the difference is it is the same cylinder, but now you see it is off axis. What does this off axis imply? It is much more higher energy. Because they are off axis, the balls are rotating in counterclockwise directions, and hence crushing is much more finer. So, if I come back to this diagram where I have this particular one, I will have ball mills. If I have this would be ball milling. However, for the higher energy one, which I showed you, where the ball milling is off center, I would be able to go down to still finer sizes. This is high energy milling. Uh, I urge you to use the wiki to its fullest power because those are simply available. Just cannot get to it. Okay, let me make a last try. Um, no. Anyway, what I would say is the next level of operation is planetary ball milling, where it is the off-center ball milling. Now, in all these milling operations, whether it is jaw crushers, you have to remember this is just 1 micron, and I am going to roughly 0.5 micron size over here with planetary ball milling. In fact, with planetary ball milling, I can go down to much finer sizes. Let me say, in planetary ball milling, what we have? We have a turntable which is rotated, and here are 3 jars. This turntable is rotated around this axis. As a result, the balls which will be in these jars, because of the very fact they are offset, as I had shown you over here earlier, they would be rotating at very high speeds, and as a result, crushing and grinding operation would occur. At speeds, here the speeds can exceed 100,000 RPM. You can easily imagine that if there are balls which are rotating around this container with ceramic powder, after some time, if I look at the inside of the container, this is the container in which it was rotating, I would see a lot of erosion and corrosion over here. I would see simply the jar being eroded. They would erode and go where? They would go into the ground powder itself. And here, using this planetary ball mill, we can produce powders which are as fine as 100 nanometers or even 50 nanometers. You have to understand, we started off from large grains, maybe the grains of sand, and from here we are coming to submicron range where the surface energy is very high. So here during this comminution, erosion, corrosion and hence contamination plays a very, very major role. Yes, people have synthesized powders this way, people in the nanometer range, but then what they have to do is, let us say they want silicon nitride powder. The jar which would contain the balls and Si3N4 coarse powder, this jar would be made up of silicon nitride. The balls would be made up of silicon nitride. Since it would require very high energy ball milling to get to these sizes, everything, the jar would be of silicon nitride, the ball would be of silicon nitride, the coarse powder would be of silicon nitride, so that no other contamination occurs. If I am going to grind zirconia, if you will see a very highly used high-end material. If I am going to grind zirconia, I would use a jar, I would use the balls, both made up from zirconia, so that during the grinding operation, if contamination happens, it would be zirconia and zirconia only. So in all these cases of crushing and grinding operation, one of the biggest problems is during this comminution process is one of erosion, contamination, which comes from the container, from the arms. In a jaw crusher it will be the jaws, in a hammer mill it will be the hammers, in ball mills it will be the balls, from there. And we have to be very careful in view of the contaminants, the way they can affect the sintering rate, how to use these mills. Today, in order to reduce contamination, techniques have been developed where the milling media, that is the, let me say the balls for example, or the rotor arms, they don't get contaminate. They are called fluid energy mills. What are they? Here a very simple example would be, if I could impact the powders with the powders, so that it is a ceramic grain which is hitting against a ceramic grain and crushing each other. They are not hitting the walls of the vessel. There are no balls, no arms to crush them, but we are forcing the powders to impact with each other and crush each other. These are called fluid energy mills, and these are the very high end usage where we require ultrafine powders with zero contamination, totally zero contamination. But that's really the top end of the product of the ceramic fabrication part. of making powders from natural sources or chemical sources. So, I have gone from jaw crushers, rotary crushers, hammer mill, ball milling, high energy milling, planetary ball milling, where particle sizes can be reduced down to almost submicron level. What I shall be next be concentrating is ball milling, because this is one of the most used operations. You see, hammer mill will reduce the particle size down to 10 to the power of 2 into 10 to the power of 10 to the minus 4 meters. Ball milling reduces it down much more usable. This is 10 micrometers to about 2 micrometers it can go down to. Most of the ceramic powders which are used are in this range. And hence, the ultimate step of most ceramic fabrication processes involves some sort of ball milling. Any one of these you can look up on the Wikipedia. There are a lot of very active diagrams I have shown to you, and you can look them up very easily. Now, before I end the lecture today, let me focus on ball milling. Ball milling. The basic process is, I have taken a jar, I have loaded with balls, whatever. These diameters of these balls are frequently, industry, the way it is sold is either 13 millimeter or 5 millimeter, oh I forgot, 10 millimeter dia balls. Frequently, instead of ball, it can be rods also, cylindrical rods of diameter 10, 13, 5 millimeter. So, what is done in this ball mill? They are about filled with, 1/3 filled with balls. These balls can be steel balls, these rods can be steel rods. There are porcelain balls for soft material. Say you want to grind talc, soft powder, use porcelain which is harder than talc. But if you want to grind sand, you have to use steel balls. Depends on the hardness of the raw material. And it is also filled up with the ceramic powder. Now what happens? As this one rotates, this outer cylinder rotates, these balls also keep rotating in the counterclockwise direction, and they keep going up till the gravity overtakes. And at that point of time, they start falling down. So this is a continuous process. The balls ride up and fall down. During this process, what is happening is, if I redraw this, they are going up here and falling back here. The ceramic powders which are there, they are all within these balls. So what is happening? The balls are rotating, the ceramic powders are within the balls. If you notice, this ball and this ball will rotate in the counterclockwise direction, because this is going up and this is going down, and the ceramic powder which falls between the balls, they are getting crushed. Now over here, this is called basically dry ball milling. That is, I have taken a jar, I have added the ceramic or steel balls, and I have added the powder which I want to grind. What normally happens in such cases is, if this is the ball to start with, as grinding progresses, we see that the ceramic powder gets stuck to the surface, and we keep seeing that this surface thickness of the ceramic powder keeps on increasing. The reason is very obvious. If this is a ceramic grain, it has cracked. This surface, which is this cracked surface, it will be very highly surface active, because I have broken the bonds between these two grains, and hence this surface will tend to stick on the ball. That is, after in this ball mill operation, at times what we see is the balls are getting coated with ceramic powder. So, the next ball is also coated with the ceramic powder, which is sticking to the surface. No further grinding occurs over here, and further grinding stops. Let me assume 3 over here. So, all of these are coated with this fractured ceramic powders. They are sticking onto the balls. No further grinding occurs. This is a major disadvantages of the dry ball milling. So, frequently what is done is wet ball milling. Here, in addition to the ceramic powder, a liquid is added, so that a slurry is formed. You know what a slurry is. During the rainy season, the soil is so full of water, it becomes a slurry. And what we have got is a very viscous liquid which has got these powders dispersed in it. Advantage is that this sort of sticking will not occur in wet ball milling. In wet ball milling, what would we expect? In that case, that is, if these are the balls, I would expect a very thin film of the slurry between the balls, and hence the grinding efficiency, the speed of grinding would increase, because as this ball rotates, what would happen? The powder would get crushed over here, the liquid would help remove it. Whereas in dry ball milling, we frequently have the problems that the fractured powder is sticking on the surface of the ball. So, essentially, we can have dry ball milling and wet ball milling. But from a personal experience, let me ask you for a caution. I was grinding alumina, and the liquid I had added was water. Unfortunately, there was no grinding action. I was not getting reduction of particle size. And then I found the answer. The answer was simply this: if this was the alumina grain, it had fractured, and there was H2O over here, what would it do? The surface of the alumina is either O minus or Al3 plus. Superb site for hydrogen bonding. So, what was happening is the grain would fracture and would get again sealed up with a thin layer of water now over here. So, one of the other aspects of wet ball milling is you have to be cautious in the type of liquid you will be using. The liquid should not wet the surface at all. I will come to the details later. in the next class. There are certain advantages of dry ball milling. The very first thing, advantages of dry milling. The very first thing is the powder remains dry. In wet, if it was wet, you would have to filter, dry, which is adding 2 more unit operations. Further, this during drying, the powders may coalesce, leading to agglomeration. So the advantage of dry ball milling is powder remains dry. Second is, as I said, talked of alumina. I was trying to grind alumina in aqueous media like a fool. And so dry ball milling avoids reaction with liquid. This is a major problem over here. You have for wet ball milling, you have to choose the liquid and hence do it. The third aspect, which is very interestingly, is less wear of grinding media and surface. You see, very interestingly enough, while talking of dry ball milling, I said that look, here's a problem. The powders tend to stick to the surface of the balls, reducing ball milling efficiency. Whereas if this was a liquid, if it was wet ball milling, this would not have happened. You would have the balls, the liquid slurry would go through and crush it. In dry ball milling, this is dry ball milling. Here, because the powder keeps on coating the balls and the container, you have got less wear of the grinding media and surface. So, whereas in wet ball milling, erosion is a major problem. That is, the grinding media, there is the balls, the container, they are also facing friction. So in wet ball milling, erosion is a major problem. In dry ball milling, because the powder sticks to the balls, erosion decreases. However, this is like a monkey climbing up a pole. You climb up 3 feet and slide down 2 feet. Fine. So dry ball milling, after some time, due to the sticking of the powder on the balls, grinding stops. So this is an advantage of dry ball milling, and because of less wear and tear on the container and the balls. With wet ball milling, I have said there are certain disadvantages. If I am doing wet ball milling, I have to filter it, then dry it. During this drying steps, the powder may agglomerate, the liquid may react, and erosion is a major problem. However, there are certain advantages of wet milling. There are certain advantages of wet milling. First of all, because I have got a slurry, what is happening is, as the balls are rubbing against each other, as the ceramic powders are fracturing, the liquid is removing the powders away from the crushing area. So, crushing efficiency is high. This is one major advantage. The other major advantage is more related to personal health. No dust. No dust. That is one big advantage. You have seen the jaw crushers, rotary crushers on the wayside. Huge amount of dust come in, personnel inhale it, and they might have even cancer. Here, because I have used a slurry, I can use very high rotation speed, thus increasing the grinding efficiency more, but erosion, major issue. I can keep on increasing the grinding efficiency. Sieving to separate into broad size range is easy. This is another advantage. Definitely finer particle size than dry ball milling. This is definitely a big advantage of wet ball milling. And I will show you later, we can have narrower particle size distribution. Narrower particle size distribution. Why? As I said, with dry ball milling, what happens? The balls get coated. So with dry ball milling, if I look at it, the particle size distribution may be this broad. But with wet ball milling, it can be this narrow, because this sort of sticking does not occur. So narrower particle size distribution is a definite possibility with wet ball milling. And why, and another reason why wet ball milling has got its advantage is, which I shall come to later, it is compatible with spray drying. I'll take this up, I've deliberately marked it in red with spray drying. This is a very important part of ceramic fabrication and processing today. Now, if I look at what I had written, advantages of dry ball milling, advantages of wet ball milling, there are pros and cons to each operation. For example, if you are in cement industry, it has to be dry ball milling. You cannot use wet ball milling. In other industries, very high-end ones, you can use wet ball milling. So there is got to be a spin-off between what are your materials, what is it that you want, to decide whether to proceed for dry ball milling or wet ball milling. I'll take off from here in the next class, but however, I urge you to use Google Images and look up plenty of literature in the net. There are plenty of Wikipedia free articles also to know more about the different ball milling operations, because this is one area which is constantly evolving, and it is evolving even today. There might be ways of milling powders which we have not even thought of even today. It's an open thing. I would not like you to be confined to books, but I would like you to explore the net.